Let's revisit that previous vector navigation problem using a concept called vector subtraction. So it's the same question we've just seen, where the water bomber must reach a forest fire that's directly to the north. And we know the airspeed of the bomber is 250 kilometers an hour in still air. And there's still a wind of 75 kilometers an hour from the northwest. And a wind direction from the northwest means towards the southeast, as shown. And we're trying to figure out what direction our plane must point so that he ends up moving along a straight line represented by that red VG, velocity with respect to the ground. We want him to end up straight. Now we know that his overall velocity is simply the velocity of the wind combined with the plane's still air velocity to make velocity with respect to the ground, as shown by the equation. But we want to solve this for Vs, just like we would do in a math class. So we rewrite the equation as Vg minus the velocity of the wind, but then we're going to rewrite it one more time and make it a plus negative. Negative V wind is simply reversing the arrowhead into the opposite direction. Since we've now rewritten it as vector addition, we can add Vg to negative Vw tip to tail as shown, and our answer, or our resultant, will become Vs, the velocity of the plane in still air. With our vector diagram complete, the question simply proceeds as it did in our previous example. Now the wind is from the northwest or towards the southeast, which automatically implies a 45-degree angle. But we need to know what the angles are inside the triangle that we've drawn by our vectors. So I use something called the Zed Rule, and I draw a couple of horizontal lines, and we can quickly see, looking at the picture, that we get a 45-degree angle as shown on our vector diagram inside the triangle. Since the velocity with respect to the ground is straight up, that would make a 90-degree angle with that horizontal line that I've already sketched on the page. So 45 and 90 make an inside interior angle of 135 degrees inside that triangle itself. Now if you'll recall, the original question asked us what angle to point the plane at so he ends up going straight. And to do this, we can simply use the sine law as shown on our virtual whiteboard. You can see how we arrange it. Sine x over its opposite side is sine 135 over its opposite side, and you simply solve for theta to get 12.2 degrees. The next step is figuring out the last of the angles inside the triangle, knowing that they add up to 180 degrees, and you can see that we get 32.8 degrees for that angle. Finally, we can switch to the cosine law to determine the magnitude of the velocity with respect to the ground, since we know an angle in between two sides. And you can see when we work it out, we get 191.3 kilometers an hour for our overall velocity with respect to the ground, as we see from below. So zooming back out, let's arrange our final answer so we can place it into words. In what direction must the plane point to reach the fire? Well, we found that to be 12.2 degrees west of the north line. And what was the plane's speed with respect to the ground? 191.3 kilometers an hour due north.